The question today is strange. Does antimatter fall up? And as you can see, the poor Newton is in front of an apple tree, and the apple is going upwards. So it's not so common, but this strange title of the talk was used by CERN a few years ago. And in fact, there are about 150 people at CERN working on this question, trying to measure directly the weight of antimatter. And in particular, I could tell you more about what I did about 27 years ago. About 15 years, people tried to measure the gravity on the antiproton, and then I showed in 1996 with some other rather well-known researchers that it was basically impossible. There are some so-called historical experiments who tried to use protons and even electrons, and then we showed that it was completely impossible. And at that time, in 96, people tried to devise an experiment that would allow to measure action of gravity, Earth's gravity, that you know very well. If you drop something, it falls down with an acceleration of about 10 meters per second squared. But on neutral antimatter, that is antihydrogen. And that was a very difficult program, which is only now arriving to completion. So first, a little quiz. Do you know anything that falls up? Have you any example of something falling up? Yes? It's a balloon, yes. Yes, that's a relatively good example. A helium balloon falls up. Yes, no, it's a good example. And in fact, then, of course, this poor helium balloon is not that negatively massive, and it has difficulty, but it falls up relatively with an acceleration, except that with the friction in the air, it does not accelerate very long. It's limit velocity, which is relatively small. If you do the same in superfluid helium, you put an electron, for example, the superfluid helium does not like, at very low temperature, does not like to be perturbed by something external with a charge. And it creates a small bubble of vacuum around the electron. Then this electron becomes negatively mass, an electron with negative mass compared to the surrounding medium, and it accelerates, and you could say it accelerates with 10 meters per second squared, like no, except that it's not true, it's 20, it's twice. Okay, that's difficult. So let's move to the next slide, which is slightly complicated. So this is the beginning, this is now. And the present view of the history of the universe. We think that the universe was very dense and very extremely hot at the beginning of its history, about 40 billion years ago. Here, it's a lot of light, very hot. But then the history of the universe in the standard model is very strange. Since the theory puts all the mass of the object above zero, positive, then you have a huge deceleration. It's a very small amount of time. And then, since you don't understand the universe, if it's completely clumpy, you need some phase that you don't really understand of. It's called inflation. Accelerated expansion, but which should start and last for only 0.34 with 0 and 1 second. So absolutely fantastically small amount of time. Then it must again decelerate very strongly, quiet down for a few billion years, and now it's supposed to accelerate again. And even some people say, well, it does not really work. I will add a second phase of early dark energy somewhere in between, which to me is, you know, that the time where people were considering that the Earth was the center of the universe and the Sun was orbiting around the Earth. But then it didn't work really well for the planets, in particular Mars, which went one direction and then sometimes went backwards. So they added what we call epicycles, circles inside circles. And that's about what is early dark energy, probably. So if you look at the sky, at the last time the universe was a star, it's extremely uniform, much more uniform than this, about 2.7 degree Kelvin, which is absolute, minus 270 approximately. But these small wiggles at the surface are extremely small, typically 1 over 100,000, the difference. So by the eye, you would not see it. It was tremendously difficult experiment. With this, in principle, you can answer the question of the ultimate fate of the universe. It's not closed. We know that it's not closed. It's very extremely likely open, which is it will continue to expand indefinitely and probably just at the limit of recollapsing, except that now it seems that it is accelerated expansion. And this accelerated expansion was completely unexpected until, let's say, mid-90s. At that time, there was a problem that the universe that people considered, called Einstein, the Cité universe, with just the amount of matter between recollapse and eternal expansion, it has the defect that it had an age of about 9 billion years, which was smaller than the age of the oldest stars that you can see, which is basically impossible, because the universe must be older than the stars in it, clearly. So there was something wrong, and then people tried to look at the geometry of the universe at very large distance. As you can see, we knew already that very probably the age of the universe was more than 10 billion years. So you have to look at the geometry of the universe, you have to look at least to 5 billion years, light years. And this was very difficult until the mid-90s again, where people look at certain type of supernovae, which when they explode, they are more luminous than all the stars in the universe for a short amount of time. They become extremely luminous and relatively reproducibly, which means that you can use them what we call standard candles, 100 watts standard luminosity candles, except that it's a lot more of watts. So let's look. It seems surprising probably to some of you, but as I said, more than one star out of two is in a double star system. So you have usually a normal star, and if you have a compact star around, as you know, the sun emits a lot of wind. This wind falls on the compact star, and after a while, the poor compact star cannot stand anymore its own weight, increased weight, and then makes a first collapse and then comes back with a huge explosion, and that's a supernova. And with this, people get a very strange composition of the universe, which I think is not correct, but that's the present stage. About 70-something, 72% probably today, repulsive energy, repulsive dark energy, because we don't know exactly what it is. Unknown dark matter, and the normal matter is only 4.5%, which is strange. And my hypothesis with some other researchers was that maybe this was due to antimatter. That's a very strange idea. And this is taken from the movie Angels and Demons, where CERN, the poor CERN, is supposed to have made 1/4 gram of antimatter, made much less than 1 millionth, 0.50 and 1 gram of antimatter for 60 years. So don't worry. But still, 1 gram of antimatter will wipe out most of Paris. And in the film, the movie, there is a parachute. They put that completely unrealistic because they would be flattened everywhere. Okay, but still, this antimatter exists, except that we don't see it in our vicinity. What I want you to keep in mind is that antimatter is negatively, at least in the theory, looks like going backwards in time, or which is equivalent also having negative energy, because that's the same transformation in physics. Changing the sign of time is also changing the sign of energy, at least in the even in the relativistic equations. So this was found by Paul Dirac in 1929 or 30. At the time, it was not discovered experimentally. So you had this strange thing that the equation said once you have a particle with mass m, you have also another particle with mass minus m, and also the charge must be reversed. If you have a charge of 1 electron, then there must be the charge of minus 1 electron. And what it is, and then it was discovered in the cosmic rays. That was relatively easy because it was inertial mass. What is much more difficult is to measure the gravitational mass. It's only now that we can make the measurement, about 90 years after Dirac. And what we are studying is this: what happens when you mix this negative mass and positive mass components, matter and antimatter. And when you look at the collapse, typically this is a big cluster of galaxies, so let's say 1 million light years. And I will show you an animation of this. You see matter collapse as usual, makes very dense stars, galaxies, etc. And then you have antimatter, which spreads out. So, as I said, antimatter is a kind of double universe. You have ordinary matter, you know it, protons, neutrons, electrons. And then, as I said, Paul Dirac found that when you make this relativistic, try to make it according to the theory of Einstein, you must have a second world which looks like a kind of matter which will have the opposite energy and will then annihilate with ordinary matter. And it does annihilate. So, as I said, when you put 1 gram of matter and 1 gram of antimatter, it's a lot of energy, typically 8 nuclear bombs above Hiroshima or Nagasaki. So that's a lot of energy. This antimatter is well detected, except that it's not in our environment. Obviously, otherwise we would be dead. There is not a lot of antimatter in our vicinity. Dark energy is something which has been invented to try to understand what is this accelerated or repulsive energy that we observe since the mid-90s, but basically 1998. When these people measured the supernovae, this type of very reproducible supernovae. But we don't know what it is. It's just a word to describe our ignorance. And dark matter is almost the same. Although I'll spend 15 years looking for it, it may not exist. Just to finish, this is an ongoing search. We don't know yet what is the weight of antimatter. We don't know yet whether it's the origin of what we call dark matter. It looks extremely promising. What we did the last 3 years really explain why you have the impression to have dark matter when there is none. It's just due to the geometrical repartition between matter and antimatter. And it gives you then the impression that you have additional matter, but it's just the fact that you don't see this very diffuse antihydrogen and antihelium, which is very far away from you. Typically from the Milky Way is relatively large object. It's typically at least 300,000 light years from you. So don't be afraid, antimatter is not so close. So for me, if you wish, I can just end with this, how it all started. For me, it started in mid-80s. Because I couldn't understand the argument about instability, energy conservation, if you have anti-gravity. And this proved to be extremely important in the following. But about the same time, there was a guy who got the Nobel Prize in between, CERN, who was asked by Carl Sagan, the well-known the guy who was doing the scenario for the film Contact with Jodie Foster, and then helped also for the scenario of Interstellar, which is much more recent, and where you have the question by Carl Sagan was, is it possible in nature to have a wormhole? A wormhole is a shortcut. Let's say you have a door between here and the moon. You describe the geometry of space, where in some books you have I don't know, Hyperion, you have many of these doors in space-time. Is it possible in physics to have such doors, some wormholes, holes which are shortcuts in space-time? And the answer is, if you can describe it with geometry, and you can, because you can make a drawing of this situation, then it must exist in general relativity. Except that you have to violate the positivity of energy. You have to accept negative pressure, negative mass, negative energy somewhere, which is called exotic matter. So then people try to look at, because people said, oh, this is impossible, it will generate paradox or global instability. And after a while, people realized that that's not true. There are no paradoxes, there is probably not big instability, not much more than what we have already in our universe, which cannot be stable. And with this came the reflection about this repulsive gravity, which found its physical implementation in '98 with the discovery of what we call dark energy, but which can also be something which is only the action of antimatter, very dispersed, that we basically almost don't see, and which is there over 50% of our universe. Okay, so that's it.